This talk is going to be about hardness of explicit constructions via cryptography. This is Jiatu Li from MIT, and this is a joint work with Yilei Chen at Tsinghua University and Shanghai Qiji Institute. This talk is going to have three parts. In the first part, we will consider the background of explicit constructions and explain what are the problems that we care about and why we need to care about them. And in the second part, we will explain our results, which is conditional hardness for explicit construction problems. And in the third part, we will explain briefly our techniques. And the main technical ingredient is a witness encryption construction inspired by public key encryption. Explicit construction problems are very common in theoretical computer science and mathematics in general. For instance, we know since 1950s that a random truth table has very large circuit complexity. And we know that a random graph is likely to be a Ramsey graph, which means it neither has large cliques nor large independent sets. And the random matrix is likely to be rigid in the sense that it's far from being low rank. However, despite that a random object is likely to have certain good properties, it's unknown whether there exists an algorithm that efficiently constructs such objects. So this is a problem of explicit constructions. Explicit construction problems have been studied independently in theoretical computer science for decades. Recently, there is a unified framework to study the complexity of the problems via a meta-problem called range avoidance. The problem is pretty simple. Suppose you are given a circuit whose number of input is n and number of output is m. The goal is to output some string y of length m such that it is not in the range of the circuit. Or equivalently, for any input x, it cannot make the circuit evaluate to the string you specify. This problem is total because of the pigeonhole principle, as long as the number of input bits is smaller than the number of output bits. Moreover, this is also an explicit construction problem, as a random string is likely to be outside of the range of the circuit. Similarly, we can also consider the restricted circuit version where the input circuit is restricted from some circuit family. Starting from STOC24, a sequence of work shows that a deterministic algorithm for the range avoidance problem, even for very restricted circuit family C, like NC0, is enough to resolve interesting explicit construction problems, including circuit lower bounds, Ramsey graphs, and good extractors, as well as rigid matrices, which are wide open for decades. The main question addressed by the sequence of work, and also in our paper, is about the complexity of range avoidance. Concretely, what is the smallest complexity class that contains a void? And if we only care about restricted circuit, what is the complexity of the problem? So why is this problem important? On the one hand, we know that an algorithm for range avoidance, even for restricted circuit, is enough to resolve many concrete explicit construction problems, which are wide open for decades. And on the other hand, a lower bound for range avoidance can be seen as a barrier in the sense that if you want to actually resolve the concrete problems, the technique cannot be general enough to solve the general range avoidance problem. Before actually talking about our result, we also need to define a variant of the range avoidance problem called remote point problem. Suppose you are given a circuit whose input length is n and output length is m. You want to output some string that is not only not in the range of the circuit, but also far from being the range of the circuit, in the sense that for every input, the string is far in Hamming distance from the output of the circuit. If the distance is small enough, we know that the problem is total by Chernoff bound. This problem can be seen as an average case variant of the range avoidance problem because you require the string to be far from the range instead of only being outside of the range. So we can also define the restricted circuit version where the input circuit is supposed to be a restricted circuit. This problem was originally defined in APY 09, where the restricted circuit family is only XOR or equivalently linear functions in GF2 as a conceptual intermediate problem towards constructing rigid matrices. In a later work, it is shown that an efficient algorithm for remote point problem can imply help function circuit lower bound, which is a generalization of circuit lower bounds. It is known that remote point problem reduces to a void for general circuit, but for restricted circuits like constant depth circuit, it is unclear whether it can be reduced to range avoidance. In the second part, we are going to discuss about the current frontier in studying the hardness and algorithms for explicit constructions and explain our new results. We first briefly survey known results on the algorithm and hardness of the explicit construction problems. On the upper bound side, Cotton shows that assuming plausible circuit lower bounds, there is a deterministic polynomial time algorithm using an NP oracle to solve the general range avoidance problem. Moreover, if we consider ACC0 circuits with weak parameters, a sequence of work shows that there is an unconditional polynomial time algorithm with an NP oracle to solve both range avoidance and remote point. Furthermore, if you consider very weak class MC0 with very weak parameters, you can even solve it in polynomial time. Here, weak parameters mean some additional constraints such as the output length is much longer than the input length and the circuit size are small. On the lower bound side, Ilongo, Lee, and Williams shows that assuming witness encryption, which is a plausible cryptographic primitive, and NP is not equal to co-NP, the general range avoidance is not solvable by a deterministic polynomial time algorithm. An open question that is largely unaddressed by previous work is that what about the complexity of range avoidance and remote point for weak class, but for standard parameter regime? The first result of our work is to conditionally resolve this problem. Extending the result of Ilongo, Lee, and Williams, we show that range avoidance and remote point for very weak circuit classes are not computable in polynomial time, assuming some plausible variants of LWE and LPN assumptions. This shows that these two problems are unlikely to be solvable deterministically, even if the input circuits are very simple. Starting from this result, we further ask whether there is a finer complexity theoretic characterization of the meta-problems. Notice that on the left-hand side, we show that range avoidance and remote point, even for weak circuit families, are unlikely to be solvable by deterministic polynomial time algorithms. While on the upper right-hand side, it is likely that they will be easy with an NP oracle. So the natural question is, what is really the smallest class that contains range avoidance? What about classes between polynomial time and polynomial time with an NP oracle? A natural class that is stronger than polynomial time but weaker than polynomial time with an NP oracle is so-called non-deterministic search algorithms. Suppose that R is a relation defining a search problem. A non-deterministic Turing machine is set to solve the problem if given an input X. If X has a solution, MX has an accepting computation path, and every accepting computation path will output a valid solution for the problem. Otherwise, MX will have no accepting computation path. Let's define a search NP to be the class of search problems solvable by polynomial time non-deterministic Turing machines. And it's not hard to show that search NP is sandwiched by polynomial time and polynomial time with an NP oracle. So our question is whether range avoidance, possibly for weak circuit families, are in search NP or not in search NP. We notice that the ground truth of the question is quite unclear. For some concrete explicit construction problems, such as rigid matrix, there is a non-deterministic search algorithm that generates rigid matrix on infinitely many input lengths. However, it is completely unclear how to generalize that algorithms to a general range avoidance problem. Moreover, this question is related to proof complexity generator, which is a very important concept in proof complexity. Indeed, we can further extend our previous result to show that range avoidance and remote point, even for very weak circuit classes, are not in search NP, assuming stronger cryptographic assumptions. The statement and the proof of the second result is very similar to the first one, but to actually prove the stronger hardness, we need to strengthen the assumptions as well as defining some novel notions in cryptographic constructions. Now we move on to discuss more formally our assumptions for the hardness results. Notice that we will have two sets of assumptions, one for range avoidance and one for remote point, and they will give incomparable hardness results, but here we'll only talk about range avoidance. The first assumption we need is called LWE against adaptive adversary. Suppose that epsilon and beta are constant, Q and M are standard parameters for learning with arrow, and W is some width bound. For at least 2/3 fraction of the matrices with n rows and m columns, there are a beta fraction of vectors of length n, such that the following two distribution cannot be distinguished by polynomial size adversary up to 2 to the minus m to the epsilon advantage. The first distribution is a uniform distribution, and the second distribution is a LWE sample, where the secret S is uniformly sampled, and the arrow E is uniformly sampled with respect to the infinite non-bound W. Note that this is called adaptive adversary because the adversary can choose the circuit to distinguish these two distributions after viewing the matrix A and V for the LWE samples. And the choosing phase can potentially be computationally unbounded. We also note that there is no specific cryptographic reason to work with infinite norm. We can also use L2 norm and Gaussian noise, but working with infinite norm can help to minimize the circuit class for the hardness of range avoidance problem. The second assumption we will need is inhomogeneous SIS against the non-deterministic adversaries. Suppose we have the same set of parameters and let ext be an arbitrary standard encoding of kappa sparse vectors, which, for example, can be implemented by a layer of AND gates. The assumption is for at least a 2/3 fraction of the vector matrix A, there is no efficient non-deterministic algorithm P or no efficient proof system P, such that it accepts at least a beta fraction of vectors of length n, and it rejects every vector of the following form, which is A multiplied by an encoded sparse string mod q. In other words, it is to prove that a given string is not in the form of a sparse binary linear combination of the rows of the matrix A. This is the notion of average case hardness against non-deterministic algorithms, and it can be equivalently formulated as the following function GU is a demi-bit generator as defined by Redick 97 as an example of cryptographic against non-deterministic algorithms. Now we are ready to formally state our result for hardness of range avoidance. Our circuit class will be a depth 3 circuit, which is called a disjoint OR of exact majority of AND gate circuits. Here, disjoint OR is an unbounded fan-in OR gate with a semantic promise that at most one of its input pairs is 1. And exact majority is a gate that outputs 1 if and only if exactly 1/2 of its input pairs are 1. AND gates is standard unbounded fan-in AND gates. And this is a depth 3 circuit where the AND layer is closest to the input and the OR is on the top of the circuit. Our theorem is under assumption 1 and assumption 2. Range avoidance for this circuit class cannot be solved by deterministic polynomial size circuits. We can further strengthen our first assumption to obtain hardness result for range avoidance against non-deterministic algorithms. The assumption is called LWE against adaptive non-deterministic adversary. With the same set of parameters, the assumption means for at least a 2/3 fraction of the matrices A, there are a beta fraction of vectors V such that no polynomial sized non-deterministic adversary will accept the uniform distribution more often compared to the LWE sample with an advantage of 2 to the minus m to the epsilon, whereas the LWE sample is still the same with uniformly sampled secret and uniformly sampled arrow with respect to some infinite norm constraint. The thing that makes the definition non-trivial is that although the adversary is non-deterministic, it is required to accept the uniform distribution more likely instead of the LWE distribution, because otherwise the trivial algorithm that guessing the secret will likely to accept the LWE distribution compared to the uniform distribution. We note that we can equivalently formulate it as the LWE function given a secret and arrow is a superbit generator as defined by Redick in 1997. It is a stronger notion of hardness against non-deterministic algorithms compared to demi-bits generator. Under the strengthened assumption 1 and assumption 2, we can show that range avoidance for the same circuit class cannot be solved by non-uniform polynomial time non-deterministic search algorithms. We note that the hardness of remote point problem can be proved for XOR of AND circuit, which is a depth 2 circuit, follows from the similar assumptions that utilize LPN instead of LWE. These two results are technically incomparable because RP remote point problem for XOR and AND circuit and range avoidance for the depth 3 circuit families are not known to reduce to each other. We note that the remote point problem for the XOR of AND circuit with certain parameter is known to be in FP to the NP. So our hardness result in that setting is actually quite tight compared to current known upper bounds. We stress that our assumptions are technically incomparable to standard lattice assumptions for example, public key cryptography. Our assumptions are stronger in the sense that we need 2 assumptions instead of only 1 for most cryptographic primitives, such as Regis PKE. Moreover, we require the security against a non-deterministic adversary, which enables a lot of algorithmic tools. We also allow the adversary in the LWE assumption to be adaptive in the sense that it can choose its attacking algorithm after seeing the query matrix A. However, our algorithm is also weaker in parameter regime because the noise is much higher compared to the standard assumptions. We note that our assumption is secure even if gap CVP for infinite norm with n to the 0.1 approximate ratio is in polynomial time. The best known attack is n over log n approximation gap CVP algorithm in NP intersect co-NP. And this algorithm is based on the geometry of the norm, so it is unlikely that it can be improved to n to the 0.1. Also, most lattice-based cryptography are insecure even if gap CVP with n square approximation ratio are in polynomial time. We know that most, if not all, lattice-based PKEs are provably insecure against the non-deterministic adversaries using the NP intersect co-NP algorithm for gap CVP. In the third part of the talk, we are going to talk about the techniques of our result. And the main technical ingredient is a witness encryption construction inspired by public key encryption. In a high level, our technique follows from the following 3 steps. In the first step, we prove that the hardness of range avoidance and remote point follows from witness encryption. Indeed, this has been observed by Ilongo, Lee, and Williams in general setting, where the circuit is general circuit and the witness encryption is for an NP complete problem. We generalize this result by looking into their proof into the problem for remote point problem, for restricted circuit, and for hardness against a non-deterministic algorithm using stronger notion of witness encryption. In the second step, we construct a witness encryption that is required by the first step from a so-called public key encryption with pseudo-random public keys. We have the following 3 observations. First, to enable the framework of Ilongo, Lee, and Williams, we only need witness encryption for certain hard languages instead of for NP complete problems. And the second observation is that most PKE schemes have some certain good properties, which we call it PKE with pseudo-random public keys. And in the third observation, we show that if you have a pseudo-random public key PKE, then you can construct a witness encryption for the PKE problem of the PKE scheme. Therefore, we have a way to construct a witness encryption and therefore have hardness of ring avoidance from PKE with pseudo-random public keys. In the third step, we instantiate a concrete construction of PKE with pseudo-random public key into the framework. Our construction of PKE with pseudo-random public key has very hard PKE problem and is skewed against non-deterministic algorithms. The constructions are follows from standard LWE and LPN-based scheme with some subtle technical changes that enables all the special properties we need for the framework of Ilongo, Li, and Williams. Due to time constraint, we will skip the first step and only talk about why we can construct witness encryption from PKE with pseudo-random public key and how we construct a public key encryption with such property. A PKE with pseudo-random public key is as follows. Suppose this is a standard PKE scheme. It is said to be a PKE with pseudo-random public key if it satisfies the following three properties. First, there is an ideal word distribution for the public key which is different from the generator distribution. Second, the PKE problem, which is a problem of distinguishing real public keys and ideal public key, is hard. Namely, the following two distributions are indistinguishable. The first one is a real public key generated by the generator, and the second is the ideal public key generated from the ideal distribution. Moreover, the encryption is semantically secure using ideal public key from the ideal distribution. We note that many well-known PKE schemes are actually PKE with pseudo-random public keys plausibly. For example, Goldrack-Mikhaeli and Regis PKE are naturally PKE with pseudo-random public keys. And if you look at their proofs, actually they first prove that it is a PKE with pseudo-random public key and then derive it's a standard PKE. Note that this is also called a dual-mode PKE or meaningful meaningless PKE if the security in ideal world is statistically secure instead of semantically secure. We also note that the encryption using ideal public key may not even be decryptable statistically. We will also need an additional security condition called adaptive security in ideal world. It means that encryption is secure using ideal public key, even if the adversary is allowed to view the ideal public key before proposing its attack algorithm. That is, the attacking algorithm can non-uniformly depending on the ideal public key. After viewing the ideal public key, the truthing phase can potentially be computationally unbounded. Our main result in the second step is as follows. Suppose that there is a public key encryption with pseudo-random public key that is adaptively secure in ideal world, then the PKE problem of the scheme admits a secure witness encryption, and moreover, the decryption algorithm is just the same decryption algorithm, the security parameter matches, and if the original scheme is adaptively secure against a non-deterministic algorithm, so does the new scheme. We note that adaptive security against non-deterministic algorithms can be naturally defined using the simulation paradigms, and it's explained in more detail in our paper. Finally, we explain how to construct a PKE for our application. Recall that Regis PKE and actually also do-Regis PKE can be seen as a PKE with pseudo-random public key. The ideal world is just a uniform distribution. The PKE problem is to distinguish the random distribution and random matrix together with a random binary linear combination of its rows. And indeed, the PKE problem is statistically unsolvable by the leftover hash lemma. The security in the ideal world is exactly the LW assumption, which is the only assumption for the PKE scheme. If you plug in this PKE into the framework, there will be three bugs. First, the LWE assumption is not secure against the adaptive adversary. This is because almost all ideal keys are real keys, which means that an adaptive adversary, after viewing the public key, can guess the secret key and propose an algorithm according to the secret key. Moreover, it is not secure against non-deterministic adversary because LWE in standard parameter is known to be in NP intersect co-NP. Moreover, there is a very subtle technical problem is that the security parameter in the ideal world is not large enough compared to the length of secret key, which is required by the Elango, Lee, and Williams framework. Fortunately, all these three issues can be resolved by one simple trick. Recall that in the key generation phase of the do-regular scheme, the secret key is a 0,1 vector x, and the public key is a matrix A together with A multiplied by x. Instead of the random 0,1 vector, we choose x to be a random sparse 0,1 vectors, which means we reduce the entropy of the secret key. At the same time, we increase the entropy of the arrow in the LWE sample, which means it's much larger than the standard setting. It is not possible in the standard setting because it will make the decryption to be incorrect. But since we reduce the entropy of the secret key, the correctness of the decryption still holds. Moreover, since we reduce the entropy of the secret key, the hardness of the PKE problem no longer holds due to leftover hash lemma fails. Nevertheless, it is still plausibly secure under the new inhomogeneous SIS assumption. The LW assumption is still secure because we increase the entropy of the arrow. Moreover, we can show that it's adaptively secure against a non-deterministic adversary plausibly. At the end of the talk, we will propose 3 open problems. First, as we already ruled out algorithms for XOR of AND remote point problem, can we show the hardness of remote point problem for XOR circuits? And this is actually the initial question people ask as an intermediate of solving rigid matrices. Secondly, if we only care about whether avoid for general circuit is hard against non-deterministic algorithms, that is, we don't really care about restricted families, can we get rid of concrete structures like lattice or number theory in our assumptions? Can we use some complexity theoretic assumptions instead of cryptographic assumptions? Finally, is there any cryptographic application of our PKE and witness encryption schemes? As far as we know, our PKE is one of the first candidates of PKE that is secure against non-deterministic adversary in a natural sense, and there might be some application of this new candidate. That's all of our talk, and thanks for listening.